This is my Physics 2211 first lab, Constant Velocity by Jeremy McWhorter. So the purpose of this lab is to analyze the motion of an object that has constant velocity. So that means it has no net force on it. And you need to determine the position of it over a time period. So we're going to base this off of Newton's second law, and we're going to create a computational model using GlowScript, as well as make a observational model using the Tracker app. So at the end, the conclusion will be that even though these two models are quite similar, the Tracker app, which is the observational, slightly varies from the computational model because it accounts for things such as friction and gravity. So these are the concepts that we'll be using in this lab. The first one is Newton's first law, which is pretty much the law of inertia. So every object will remain at rest or in uniform motion in a straight line unless compelled to change its state by the action of an external force. It's a way of saying what an object that is in motion will stay in motion unless acted upon by an external outside force. Emphasis on the external portion. It's important to define your system when you're talking about experiments such as this. So our system will solely be the bottle because that's what is included in the computational model. And then the other one is Newton's second law. So that's what you can see up at the top, which is F net equals ma. So because the F net is going to be equal to 0, that means, because we're going to be have a constant velocity, that means the F net will be equal to 0. But Newton's second law is that force is equal to mass multiplied by acceleration. So yeah, once again, an important concept here is that even though the object is still moving, it's moving at a constant velocity, which means that it has an F net of 0. So pre-lab, the object I used, it was an empty Yeti bottle, and it'd be what I would track. So the Tracker application is what tracks the video I took of the Yeti moving, and then the GlowScript application is what produces the computational model using code, which is Python. So here are the values that I used: the mass of the bottle, the diameter, initial position, initial velocity, and then the frames are important because that's how I tracked it using Tracker, and then the final time, that's just, there are 51 frames in 2.1 seconds of it moving across the screen. So here you can see the video of me moving the water bottle. You can see the axis is centered at 0, 0, which is the center of the bottle. And then the ruler at the bottom, which tracks the distance it goes. The graph over here shows it starts off pretty linear, but then it kind of tapers off at the end because that's when friction and gravity start working on it. So this is the Tracker, which is the observational portion. And then this is the GlowScript right here. So the code starts here. Most of this was just from the sample code that they gave you, and then you just had to make slight variations to the initial position and velocity. So it uses a while loop, which is a form of iteration, and that computes it using the velocity update formula. One thing to keep in mind is that this is purely computational. Once again, I keep reiterating this, but it's because it's purely computational, the results are linear because it has no effect from forces outside the system, such as gravity and friction. So yeah, because it lacks the outside forces, it's a straight linear graph. And then this is how we expect the bottle to move rather than how it actually moves, which is what we saw in Tracker. So this is the GlowScript. And then here's a comparison. The dotted lines are the experimental, and then the straight line is the computational. So as you can see, they start off pretty similar, both pretty linear, but then eventually the observational points kind of taper off, showing that they're being affected by other things outside of the system. The reasons for these differences could be maybe I measured the weight of the bottle wrong or the distance wrong. And the other reasons could also be that the error within the Tracker system itself. So one of the questions we had to answer was, what if the axis was flipped? If it were flipped, the bottle would then travel in the negative x direction instead of the y direction. This is shown with the negative slope of the graph. The speed would be the same because speed's a scalar, but the velocity would change because the velocity takes sign into account. So the bottle will travel in the negative y direction too. So pretty much what we covered. What does this all mean at the end of it? This really illustrated the difference between computational and observational data. The observational data will always have forces outside of the system acting on it. And this also illustrates that even though the bottle was moving at a constant velocity, it still had a net force equal to 0. And then conclusion, so we created a computational and observational model, and then we compare the two models, and then we also utilize both Newton's first and second law, which are both displayed here again.